space is moving away from being a purely government activity, but also it's moving away from being this sort of safe, peaceful high ground to what is now, a contested warfighting environment. Well, right now, it kind of is every player for themselves. And what we really want to see as it expands is, in fact, international norms, rather than just sort of the land grab that's going on right now. Well, these complex space products, they take a decade to develop in field. And so it takes decades to grow that really deep expertise.
Hey, welcome back. I have been really happy. I've been thrilled about this podcast for the last couple of weeks. I'm happy to have the CEO of United Launch Alliance with me. Tori Bruno is an incredibly accomplished aerospace executive. He's been the CEO of ULA since 2014. It's amazing how far you guys have come, Tori. 155 launches now?
Coming up on 165 on the next one, in fact.
165 launches, Vulcan rocket. You're working with Keeper now, or Kuiper. I never knew how to pronounce it.
Kuiper. Amazon Project.
Amazon Project Kuiper. The one thing very few people realized you did was you led the transformation, from Russian engines to back to the U.S. Not a lot of industry, not a lot of press on that at all. But and here we are. It's a great day for. It's an incredible era for the space industry. So thank you for coming on.
No, my pleasure. And it is a great year for the space industry, and not just commercial, but for the government, broader industrial base. So many things happening. It's very exciting.
Project Kuiper. Golden Dome now, a lot of focus. I take it you're going to play a big part in that. Commercialization, a lot of people talking about the commercialization of space, data centers, space-based data centers. Obviously, we've got all sorts of, satellite communications going on around the world. Where's it all go? Where's it all going? I mean, what's the new frontier going to look like?
Yeah, well, it is exciting. And kind of the really striking thing about it, I think, is there's sort of two flavors to it. There's kind of like, I'll say the good news, and then there's the more challenging news. And, I'll start with the more challenging news so we can end more positively on that thought. On the one hand, space is moving away from being a purely government activity, but also it's moving away from being this sort of safe, peaceful high ground to what is now, a contested warfighting environment where I think it's likely that if there is any kind of even limited conflict with Russia or China, it actually starts in space. And so that's a big change in something that is really unfortunate, that there are now lots of anti-satellite weapons, both on orbit and on the ground. And it's something we have to be prepared for if we're really going to keep the peace and deter that kind of aggression. So that's the challenge. Now I'll flip that to, and at the same time, space is commercializing at an incredibly rapid rate. And there are more spacecraft on orbit right now by about a factor of 10 than there have ever been. And that future is really bright.
I was with the folks at Satcom Direct probably about 8 or 9 years ago. And we were just talking, and they said, the cost of launching a satellite has come down by a fact. They're exaggerating, like, CEO of Satcom Direct was like, the cost of launching a satellite has come down by about 300% since, whatever. It's now very viable to put up. Is that cost? Is that going to continue to, is it going to continue to come down?
It will continue to come down, but that statement is very misleading. Because I think when most people hear that, they think the cost of launch has come down by 300%. And that's simply not true. The price of launch has come down anywhere from say a factor of two, maybe 2.5. What has come down by even larger percentages than that, more like a factor of 10, is the price of a spacecraft on orbit. And that's all about the spacecraft, not about the launch service, actually. The new thing in the industry is this very small spacecraft that has really pretty good utility, far better function than you could ever put on a satellite of that size before. And that allows you to, instead of launching 1 or 2 satellites on a heavy class launch vehicle, to be able to launch 20 or 30 of them. That's the big lever. That's the factor 10, even factor 20, depending on what we're talking about. And the application for that is, of course, the low latency internet that is parked in LEO.
So is the LEO where the big focus, beyond LEO, where's the focus going to go? Low Earth orbit, satellite connectivity.
Yeah, that's the focus right now. The space, I'll say the commercial space is completely dominated by that. And as you pointed out in your question, that is in fact dominated by internet in space. So low latency, high bandwidth, high throughput. And they all go together in the physics. If you want to have high speed, you need more than just bandwidth. You also need low latency, which is the time it takes to communicate to and from your network. And when we move that communication from GEO, where it is prior to now, into LEO, it's literally 10 times or 1/10 the latency. So 10 times faster in that two-way comm. But when you're in LEO, the satellite's only over your head for about 5 or 6 minutes at a time. And so you'd have this blazingly fast, internet connection to space for like 5 minutes and then nothing for an hour and a half, which would super suck. So instead, you have to have a satellite always over your head. So the instant one is starting to move off of you, there's already 1 or 2 on you again. And when we do the math for that in LEO, that means these constellations are in the thousands of satellites in order to make that happen. And that requires that many satellites to be lifted in just a handful of years to get your business going. And therefore, they have to be tiny. And so they can go in large numbers, dozens at a time on these heavy class launch vehicles. And that all works together to create that scale that has made the price so low. But it really only applies to those kinds of tiny spacecraft, which at the moment are really all about LEO and internet connectivity. As we look forward into the future, your other question, I think we'll start seeing some proliferation in GEO as well. Those satellites will be bigger. They won't be quite as small as what we're doing right now for internet connectivity, but they'll also go up in multiples, not quite as many. So that market will open up within the next 5 or 8 years as well.
Interesting. So let's talk about, let's go back to your original, you said kind of the challenges of space right now. It's the new frontier, and we want, the United States, China, Russia, Japan, North Korea are all trying to, we're all competing for the same, however you want to call it, the same outer Earth orbit.
Real estate. I mean, you can think of it as real estate.
How does this all get worked out? International protocols, or is it going to start to be every man for himself or every country for itself? Or how do you see it all playing out?
Well, right now it kind of is every player for themselves. And what we really want to see as it expands is, in fact, international norms rather than just sort of the land grab that's going on right now. And the thing that is also unique about these proliferated constellations in low Earth orbit is it's not like other uses of orbits where there's relatively few spacecraft and they'll be spread out, around, not just around that orbit, but at different altitudes. These constellations are in thin, densely packed shells. And you really cannot cohabitate, if you will, with somebody else's constellation. That altitude band is owned by the one who gets there first and is using it. And we're seeing some really crazy behavior and kind of internationally in the marketplace created by that. If you went and looked up licenses, both here in the US and in Europe, which is the other main body, China almost doesn't count because they do their own thing. They don't license with anybody else. You'll see these crazy land grabs by countries that are not even spacefaring nations, and they're counting on sort of buying up the real estate, holding the license for the span you're allowed to. It varies, but let's say 3 or 4 years, and then hoping a legitimate company comes along and is forced to buy it from them. So what we really, really need is absolutely, yes, a set of international norms and behaviors on, what orbit you'll be at, whether you will do controlled reentries of these spacecraft at the end of their life and not just cascade through everybody else's shell on your way back into the Earth. Because in these orbits, these are not stable. So when the spacecraft is run out of fuel and it's done, it will deorbit and re-enter into the atmosphere. And when we've got tens of thousands, you'll be talking about multiple re-entries every single day.
And space junk, not to mention.
And lots of space junk. And God forbid that there is a collision within one of these adjacent or within one of these single-use orbits, because, with thousands, which is the typical number. So these constellations typically will have thousands of spacecraft, and they do already. There are multiple close approaches every day, and the spacecraft themselves are only separated by, say, 20 to 30 kilometers at any moment in time. So if you have a collision and you create a debris field that is more than, say, 20, 30 kilometers across, it'll sweep through a good hunk of that shell. And then you'll have a big orbital debris cloud for the length of time it takes at that altitude to deorbit, which could be months or even years in some cases for the higher ones. So we absolutely want to have rules. Are we driving on the right side of the road or the left? What is a reasonable amount of spacing? What are you going to do when you approach end of life? Or else we have the very real possibility of what we used to talk about as the Kessler syndrome, where you have this big cloud of debris at some altitude that's very difficult to fly to the other side of.
Do you see, the commercialization of space, do you see a lot of standardization starting to take place? Is it,
Yeah, it's the classic first mover thing. The folks that get there first, Starlink, Kuiper, OneWeb, what they do becomes the standard that everybody else conforms to. And I don't want to paint too dire a picture. The operators have a pretty vested interest in acting reasonably, responsibly, because they'll be the first ones impacted by poor behavior.
Yeah, no doubt. I mean, it's always fun when you see the new frontier being developed, and much like the internet. Here we are. So look, your technology has changed incredibly over the years. Satellites are more powerful. Rockets are more powerful.
Yes.
What's driving the new, not what's driving the new technology, but how's the new technology?
Really exciting time to be in lift and space in general. But, just starting with the notion that, the rocket is really cool. And here we love rockets for rocket scientists here at ULA. But the reality is the rocket has no inherent value. It doesn't do anything of itself. Its role is to take a satellite into orbit to do some important mission. And so it's really all about satellites, and where the satellites are heading is what really drives the need for changes in technology and advancements in the launch vehicle. And in our world, in ULA particularly, there's a big division in the types of launch vehicles that people develop and fly. There's really only two kinds at the highest level. There's launch vehicles that are fully optimized to finish their mission when the rocket is in LEO. Now, the spacecraft might go higher or further, but it's been dropped off in LEO. The rocket's done. And then there are other missions where the rocket is going to carry the spacecraft all the way to some other orbit beyond LEO and drop it off there. And that fundamentally affects sort of the architecture of the rocket and even the smaller, lower level technologies that are present in it to make it work. Everybody has really gone after this LEO market we've been talking about, and all those rockets are optimized for that mission. So an Ariane, a New Glenn, a Falcon, even a Starship, when it reaches orbit, they're all really focused on finishing their mission there. And then we have Vulcan, our new rocket. We're the only one who have continued to have an architecture that is best optimized when we go direct inject to something like GEO. And which is good because you really kind of need both. You need both in the marketplace. But what it's done to us or for us is said, okay, great. You have optimized a basic vehicle for these most exotic orbits, which, by the way, are pretty much only used by the government, only rarely used by a commercial company. So what are you going to do to also be viable as a LEO lifter like we are for Kuiper? And for us, that meant kind of cheating the rocket rule a little bit in having a modular rocket where we can have these strap-on solids that can be there or not be there, more of them, less of them, two different kinds of upper stages so that we can be really, really good at that high energy orbit, but also still competitive down low. And as we roll forward, we're going to have to continue to update our Vulcan rocket. It can't be static anymore. So, for example, we have a very, very long duration upper stage. That's one of the key elements that allow that direct inject high energy stuff to work. The upper stage, it's got to be comfortable going 12 hours, not 1 hour. And so if you start from there, there's all kinds of missions in the future in space that would love to have a big, powerful, fast upper stage that could just last a really long time and fly around and service spacecraft or relocate spacecraft or, God forbid, interdict, attacks that are developing in orbit from China on one of our assets. So we're off pushing that all the time, extending the life. It's 12 hours now. It's going to be more and more and more, and it's going to be able to do all these other missions. Meanwhile, we love that booster, but that booster flies all the way into space so it can hand off this fully fueled upper stage to go somewhere beyond LEO. Nobody else does that. They all flow to a lower altitude and stage there, which makes it easy to fly the booster home and reuse it. So we have to have a completely different approach to reuse. And make no mistake, everybody needs to be doing reuse, including us. You haven't seen us do it yet because we just finished the rocket. You got to build it first, then you got to reuse it. So we have really cool ways of reusing, some of which I've talked about, some of which I haven't, that are kind of a secret right now. So watch this spot.
So more to come on that, huh?
More to come.
What's developing? What's driving? Is it advancement in different types of rocket fuels? Is it the same rocket fuels, more is better, with a different type of payload? What's the technology looking like?
Yeah, the fuels have not become necessarily better in terms of performance. Chemical propulsion is still it's still liquid oxygen, liquid hydrogen is the highest performance possible. That's what we put on our upper stage. What's changed is the introduction of a lower cost, more available fuel. Similar performance as to what we had before, but just a lot more available. And that's methane, which is a form of liquefied natural gas. It's a purer form. And when you look around, you'll see everybody has kind of gone to that for their booster, for their first stage. And a lot of them have gone to that for their upper stage as well. We've stuck with the LOX hydrogen because of that special mission our upper stage does. It really needs the most energetic, highest performance fuel there is. And that has helped and contributed a little bit to the lowering of cost of the boosters. Is the availability of or the ability to use this fuel. Why didn't it get used before? We've had liquefied natural gas forever. Methane as a propellant has been available, and the answer is because it was really hard to develop engines that could use it and use it reliably. Any hydrocarbon can be flowed through a rocket engine, but these devices are just so powerful and so compact. To give you a feel for it. So one of our, BE4 methane powered rocket engines, we use two of them on the first stage of a Vulcan. One of those is a bigger power plant than you have in an Aegis cruiser, in a giant ship, where that engine compartment is, as big as your house. This thing that's like the size of a refrigerator has got more horsepower in it. And so when you're burning those propellants to make all that happen, there's just so much energy. Just the acoustic energy alone in the combustion chamber, if it's slightly unstable, think, like in a cold day when you start your car and it's idling and it kind of idles a little rough. That's kind of like the same phenomenon that we talk about in rocket engines when we talk about acoustic instability. The only difference is in about half a second, that roughness can explode the entire engine because there's millions of horsepower in that thing, in that tiny little thing the size of a refrigerator. And methane is one of the propellants that tends to be a little noisy. And people had been trying to develop methane engines for decades and decades, and you could never get above a certain size before that phenomenon just took over. And that has been solved just in the last few years to be able to get to bigger scale rocket engines. And that's what's allowed us to bring natural gas, or in this case, really methane, which is a cheaper, more plentiful, domestically produced propellant, into this arena.
Is that technology, obviously proprietary to you guys?
No, actually, you've seen it spread. Our engines were kind of the first to solve that problem, but everybody's doing it now.
So the technology is kind of more through the industry.
Exactly. And so what that means is that sort of niche thing, that propulsion technology that uses methane, that's become common. And so what is now the competitive differentiator is how you architect the bigger rocket, how you put all the pieces together. Whether or not you're doing the high energy exotic orbits, whether or not you're doing orbits that let you do flyback boosters, that's the innovation that the companies have had to branch into and explore instead of something as narrow as just what propellant can we use in your engine.
Do you see, as the technology becomes more prolific throughout the world, do you see, you guys, obviously, Elon's out there. I just saw Japan launched something not too long ago.
Yeah.
Do you see a couple of competitors to ULA, or do you see more, a more burgeoning industry?
Yeah. It's actually still smaller than I think people think. So, in terms of the big hunk of market, the big hunk of market is the largest single market in lift, is really owned by heavy class launch vehicles. That's where all the missions are. And in that arena, there's only 4 worldwide, and there's only 3 domestically. So there's Ariane in Europe.
Mm-hmm.
That's the one that is not U.S. And then inside the U.S., there's SpaceX, ULA, and Blue Origin with the New Glenn that will be coming into the market very soon. And when you do the market analysis for that, that's really all that can be supported, just that 3-ish kind of number. Now, there's a whole nother market for what we call micro launchers or small launch vehicles. And at one time, people imagined that was going to be gigantic. When they were first contemplating these LEO constellations you and I have been talking about, 3,000 spacecraft on orbit, people said, hey, I can make a small launch vehicle that'll launch just one of those for a fraction of the cost of these big heavy class vehicles. Therefore, there's a marketplace out there of thousands of launches, maybe tens of thousands. And there was just one flaw with that, and that flaw was physics. And in fact, there's a factor of scale in rocketry. You'll hear people say the rocket equation, and that talks about, how the payload in the vehicle are related in size, in performance. And the reality is a heavy class launch vehicle on $1 per kilogram to orbit is 10 times more efficient than a very small launch vehicle. And so, yes, you can launch a single spacecraft to orbit for, a small fraction of what the big launch vehicle costs, but the launch vehicle's taking dozens. And when you do the math, it's just way, way, way cheaper to go on the big vehicles. And I'll tell you a story. I went to a conference a number of years ago in Santa Clara, for all the new launch vehicles. I sat on a panel, and it was this big, exciting thing where there was, at that time, 127 or 28 small launch vehicle companies registered, and they all came to the conference, and we're all on the panel. And I sat there and I said, well, you're all going out of business. The market for you will sustain 2 or 3. So out of 128, I'm expecting 125 of you guys to be here in about 8 years. And they booed me.
Yeah. It's like the eVTOL industry right now. So
yeah. Well, here we are. We're about 10 years after that conference, and we've got Relativity and Rocket Lab and maybe Firefly.
Yeah.
And so there's like 3 or 4 hanging out. And personally, I think there's room for about 2. And I'll pick Rocket Lab as one, and I don't want to pick the other one because I'll hurt somebody's feelings.
I got you. Okay.
It can't overcome physics.
As I tell my wife every day when she's like, can you make it quicker? Like, no, I can't change physics, baby. I can't change physics.
That's right.
Let's shift the subject a little bit. Let's talk about hypersonics. I got to think you guys are, big DoD focus on hypersonics, and everybody's talking about hypersonics and transportation. I got to think that's weighing on your mind a little bit.
Yeah, well, it's really a golden dome question because, when we say hypersonics, it's because it's easy to say. It's harder than to say maneuvering hypersonics because all these rockets are hypersonic, always have been. And when you hear people talking about hypersonics, they're really talking about a missile defense challenge. And what they're referring to is a maneuvering hypersonic threat, most of which are gliders. And the reason that is significant in a missile defense context is because of the way we do missile defense today with the technologies that are available. So you have this thing being shot at you, a ballistic missile typically. It is, of course, hypersonic. But the important thing is that it follows a ballistic predictable trajectory from when you detected it until it impacts on its target. And to stop that, we use an interceptor, which is another rocket. You want to stop something flying at rocket speed, you better use another rocket. And so it's a little bit like shooting trap, if you've ever done that. You see the thing launched, it separates very early from its rocket. It's now going rocket speed, hypersonic speed. And you see where it's going to go. You lead the target, you launch an interceptor off another rocket. They arrive at the same place and you hit it. And in fact, that's the most effective technology is, in fact, what we also call hit to kill. These interceptors don't have warheads on them. We have such exquisite technology. You can literally fly out hundreds or thousands of miles at something traveling faster than a bullet and intercept it with another bullet and literally hit to kill, literally hit it. And that's how we do it. The problem with this maneuvering hypersonic threat is it can wait until you commit the interceptor and then maneuver. And you fly right by and you miss it. So that's the big challenge. And that's part of what Golden Dome is going to have to contend with. Now, fortunately, 80% of the targets that would be thrown at us today, 80% of the threat is ballistic. We have exquisite ballistic missile defenses. We just need more of them to do a comprehensive defense of the U.S. We don't have that today. I think a lot of the public imagines that wherever they are at this moment, they are protected from a ballistic missile attack from North Korea or Iran, God forbid, Russia or China. And they don't realize that, no, they're not. And there's a lot more countries than those two that might choose to attack us and currently have ballistic missiles. That's why Golden Dome is on the table. By having more of what we already got, we address that ballistic threat, but we are still vulnerable to the maneuvering hypersonic threat. And that's going to take a little bit more time and really heavily involve space, in my opinion. There's two things that you have to have that are special for that threat. You have to have continuous custody of this glider or whatever the hypersonic vehicle is that's coming in, because it's going to maneuver. You got to be able to see the maneuver and always know where it is the entire time. And then you have to have something that can cope with that maneuver and not be spoofed by having it move on you. When it's traveling at about the same kind of speed you can travel to hit it. And I have been advocating that the best way to do that is to have a space-based directed energy solution, a laser, basically a space-based laser, because nothing outruns the speed of light. Maneuver all you want. And of course, if you want continuous custody, that is also a space, application, because that's really the only way to do it. You can't do it with ground-based radars. Because the horizon is too short. To have a 2,000-mile horizon to be able to see anything approaching the United States, you've got to be on top of the tallest possible mountain, and you don't have super tall mountains everywhere you want them. The only way you do that is from space.
Is that feasible? I mean,
Absolutely.
when you take the budget, into account, and
No, it is. And in fact, the Space Development Agency, SDA, is already working on that continuous custody, or what we like to call in the missile defense world, birth to death tracking. They're already working on that now. They're developing spacecraft. They're beginning to populate a LEO constellation that would do that. So when you hear SDA tracking layer in the press or in the Pentagon, that's what they're talking about. You'll also hear them talk about an SDA transport layer. Well, these trackers are going to be in LEO. And that means you got to move the data around. Remember our discussion around the satellites only in one spot for 5 minutes, right? So that means you're constantly sharing data between the spacecraft and the battle management system. That transport layer is another LEO constellation that's moving the data around and getting it to shooters. What is not practical is to have all of that in place within the next 3.5 years, which was the time frame the president set for a horizon on Golden Dome. That's why you got to start with the terrestrial systems that we already have in production right now to get that initial defense. And then we add the space layer, which will take a little bit longer than this president's term. We also need the shooter, so I'm back to where you have kind of two choices. Both of them are in space for the hypersonic threat. One of them can be hit to kill from space, really good for the ballistic threat. Some advantages, it's inherently global. These LEO constellations, they orbit the whole Earth. You can't hover in LEO. So
Right.
you're inherently global, and that lets you potentially identify and engage these threats when they're closer to the adversary's territory, maybe even shoot them down when they're still over their own land. That's attractive for a whole lot of reasons. But I favor the directed energy because a hit to kill, even based in space, is not as effective against the maneuvering threat. It's still only traveling at orbital velocity, which is only perhaps a little bit faster than the ballistic threat is going. Whereas directed energy, a laser in space, nothing outruns the speed of light. It might as well be standing still from the standpoint of the interceptor, if you will. And that
So
technology is now coming into its own and becoming practical.
what's the most challenging development of that technology when you think about it? Is it communications between the satellites? Is it the directed energy? Is it the lasers? Is it the
Yeah.
lasers? Is it the
It's the lasers. And
okay.
what is the challenge for the laser that made it impractical before is the power source that generates the photons. Making the laser was the hard part. And in prior life, before ULA, I was a missile defense guy, if you hadn't guessed already. And I had this really cool program called the Airborne Laser.
Sure.
And so if you've heard of it, I mean, super cool, right? 747, giant multi-megawatt class laser. We would be able to fly around and on an enemy's border and blow up their missiles when they were still in boost phase. It was a really cool capability. And President Obama canceled it because he said it was impractical. And if I'm completely honest with you, Craig, he was not entirely wrong. 2/3 of that 747 was essentially a liquid rocket engine burning propellant to make photons, a chemical oxygen iodine laser. And that had certain logistical challenges associated with it.
Yeah.
And so what has changed since then is the coil goes away. We now have solid state electric lasers that can make those photons without all of that, without chemical combustion. If you have electricity, you can have high powered lasers. That's the new technology that is unlocking that. And in space, we don't need multiple megawatts of laser energy. We're down in the tens of kilowatts power range. And that is practical to do in space.
And I take it that is all developed via, sun, sun.
Well, it could be, yes. It could be large solar arrays that charge capacitors for a shot, then a pause, then a shot. But, modular nuclear power is becoming practical for space applications that would allow us to have continuous fire or even a chemical source, something like, remember I talked about my big, giant, high power, fast upper stage with lots of endurance. Mm-hmm. Something like that where you burn propellants to run a generator would also be practical for that application.
So we just talked about technology, and you talked about, all right, solar, solid state lasers, nuclear energy, which is can be very compact. Things 20 years ago, people would have said here we are, 2025, 20 years ago, at the turn of the century, people would have said you're nuts.
Yes. Well, thank goodness a few people just were comfortable being called nuts and kept working on it so that 20 years later, now it's ready for us to, finish off the development and have.
What's got you most excited? I mean, obviously we're talking, that's, pretty cool programs. What's got you really excited about, what you guys are doing? Is it this program? Is it the Golden Dome? Is it the commercialization? Is it, a lot of people say, hey, we put data centers in space and they run in a cooler environment.
Yeah, it's the commercialization. Golden Dome, I gotta be honest with you, for ULA, that's not a big play for us. There'll be things going to space. We'll compete for them with the other companies and, we'll get some of those lifts. But the reason I talk about Golden Dome a lot is because it's complicated, hard to understand. I happen to be a missile defense expert independent of my role at ULA, and I just try and help explain it to people so that they can grasp it and make good decisions around it. So what is something interesting for ULA is this tremendous commercialization. We're seeing just the tip of the iceberg with these proliferated LEO communication satellites. But as we bring the endurance that, say, is associated with nuclear propulsion and the other technologies we have in our long duration upper stage, we're going to unlock a whole host of commercial activities in space that are not just communications or data. You talk about data centers, absolutely. but there's also manufacturing of specialty things in space, especially materials that you can't make in a 1G environment, just can't make them. There is tremendous natural resources. We can start with the moon, where we have industrial metals and precious metals and water, which is propellants, so that you have the transportation system that enables all that are in just astounding quantities, imagination-defying quantities that are in shortage here on Earth. And as we go a little bit beyond the moon to what we call the near-Earth objects, or the asteroids that are really orbiting Earth or near Earth, just beyond the moon's orbit, it's destiny changing for our species, how much resources are there. And, one of the ways to think about it is, when we talk about scarcity here on Earth and smaller footprint and all of that, what we're really talking about is just trying to live within the finite resources available to us here on Earth today, in full knowledge that they're still finite. Even if we slow down our rate of consumption, someday we run out and civilization collapses. All we're doing is delaying the eventual collapse of our civilization, which is a pretty depressing thought. And yet, a week from where you and I are sitting in our offices having this conversation, there's an imagination-defying abundance of material that change that entire equation. All we need is a practical way to, be able to go out and get it and transport it back here. Just a transportation system in space, like the interstate transportation system here on Earth, like the sea lanes, like the railroad. We need a railroad in space. And the technologies to create that, they're going to happen in our lifetime, Craig. This is the really exciting thing.
That's crazy to think. That brings up a whole nother issue. You talk about minerals on the moon. How are we gonna? The moon's an international. It's kind of an international asset. How do you divvy up? And once again, is it going to be first come first serve, or how do you figure that one out?
Yeah, well, we need a regime, because the only legal regimes we have now say, well, you can go to the moon, you just can't take anything off of it. And if you take anything off of it, you sure as hell can't sell it. Well, that kind of puts a damper on mining.
Right. I would think so. So the bottom line is, what's coming is, most people haven't even thought about what's coming down the pike yet. But
that's right.
But it's coming.
Absolutely, it's coming.
A little like AI, and a little bit like AI, and where the internet's gone, and et cetera. It's all coming.
Yeah.
Where are you finding the technology? Let's talk about the people a little bit. Where are you finding your scientists? And where are you finding it's making rockets is complicated?
People are a funny thing in the launch business, because if you look at it as a business, you see stuff. You see really expensive stuff. There's, the infrastructure, you get your rocket factory, and you've got your launch sites, and you put all that together, and it's really expensive. There's like $5 billion worth of infrastructure to launch, even at the rate we launch with the kind of vehicles we launch. And then you go, well, what's it cost to develop a heavy class launch vehicle? What's all the IP worth? And you talked about, we're introducing Vulcan. We retired the venerable Russian RD-180, which means Atlas retires. Well, the IP is worth another, say, $5 billion. And so just the things, the physical things, there's $10 billion worth of hurdle and value in a launch business. And here's the big secret. The third thing in your business is, of course, your people. And that's actually the important and valuable part, because the physical infrastructure is absolutely worthless without.
Mm-hmm.
You've got to have folks who have the skills and the knowledge to use that IP and that physical infrastructure. And they've got to have the right culture and the right attitude to do the kind of work that we just talked about doing. And so it's really easy for businesses and for investors to really focus on those physical things because you can see them, you can measure them, you can put a price tag on them. But the real secret is it's actually just still all about people. Like almost every other business there is, people are the valuable thing. And I would say even more so here. So before this was a broader industrial base where we might share talent back and forth. When we were just on our own, when I first came to ULA, all of that talent was built organically over years. It's not like the tech industry where a product gets conceived and finds itself on a shelf 18, 24 months, man, a really long one's like 3 years. Oh gosh. Well, these complex space products, they take a decade to develop and field. And so it takes decades to grow that really deep expertise. And that means that, the infrastructure, the IP, super important, pay attention to that. But if you are not valuing your people and understanding where the skills lie and building an environment where you're growing new people all the time, then you're not going to survive very long because when your guys retire, your old guys retire, if you haven't been growing new ones and you're now a decade away from having somebody, you're kind of toast. And so if you come to a place like ULA, we really, understand our critical skills. We know who's got them. We value those people. We make sure that they are training other people who are continually improving their career. We worry a lot about retaining them and making sure that they have the right culture. I'll come to culture in a minute. But I'm going to tell you about something we haven't talked about much in the public that we started a couple of years ago that I think is really cool. You hire engineers, rocket scientists from the best universities, but they just have the foundation. Right. Even the universities that teach rocketry, they don't really know how to do it because you can't have those skills without using them. If you're not doing the real work, the skills themselves are not real. Mm-hmm. They're academic in nature. And so when you get them here, they have this big, long, career-long, lifelong learning that is in front of them. Well, I created a couple of years ago this thing we call ULA University. And so it's entirely internal. And we took all of our really smart guys and we said, hey, what do you know that we need? And how would you organize that into a curriculum if you want and teach others? How do you teach your mentees that you teach? And we structured the whole thing into specific disciplines. You want to be a trajectory guy? Well, these are the things you got to know. And some of them are academic in nature. We teach them. We teach our own classes with our own experts. But a lot of it is project-based and learning on the job and being guided through assignments that develop those skills for you under, sort of hopefully the watchful eye of experts who are literally world's experts in these topics. And we have it arranged in a way that you can earn credentials and you can advance through certain levels of competency and be recognized for that, awarded for that by the experts who are training you. And it lays out a career path, which is one of the things that young engineers really, really want. I don't know if you encounter this in your world, but this generation, they kind of want to understand the path laid out in front of them so they can go be self-directed and executed. They want to be able to level up every year or two and know that they've done it. So we organized it that way so that they can do that. And our people just love it because not only do they have that ability to direct their own career, they feel like you're investing in them.
There's a little Silicon, down the back of my mind, Silicon Valley is notorious for raiding each other. Big Wall Street Journal article
in this industry.
I was going to say, our people, it must be a constant game of cat and mouse where you've got the known top players, obviously it's a high level skill set. Who does really well? Who does really well? Is it, you've got, is it the engineers or physics? Is it mechanical engineers? Is it,
Oh, yeah. Yeah. So rocketry is an applied science, right? So you need applied scientists. Those are engineers. Our rocket scientists are, for the vast majority, have engineering degrees.
Mhm.
And in aerospace, there's top four. It's always that four or generally in this order: mechanical, electrical, aero,
Mhm.
and then software. And sometimes aero and software, computer engineering trade places. Those are the big four. They're not other things. There are very few environmental engineers in a rocket company and so on. It's those four. And, the industry is matured enough now. We were talking about rating our people back and forth. At least we rate our people back and forth. When the competitors were standing up their capabilities 10 years ago, ULA was it domestically. And so everybody came here and stole my people.
Right.
Where were you going to stand up a launch team from? Well, you had to go to ULA. That's where the launch team was. So, but now it's different. So I have people that leave ULA and come back, and the same, I think, with the competitors. And, people are really careful about proprietary data and stuff like that. So don't misunderstand me, but it does create cross-fertilization and in a way that helps the whole industry move forward faster than it would have otherwise.
MIT, Georgia Tech, Cal.
We like those. We like all of those. We like Purdue. They have a great propulsion program. We like University of Texas, El Paso. They've now got a great additive manufacturing and propulsion program. Blue has helped them a little bit because their main test site is down in that part of Texas at Van Horn. We love Cal Poly. I don't know why. I don't know. Maybe the CEO went there, but that's a really good university. So, the other thing that you consider when you're this kind of technology company is also where your facilities are. Because statistically, people will settle. They might start somewhere else out of school, but they settle and stay either where they grew up, where they're from, or where they went to school. And it's kind of divided evenly. But a solid 70 to 80% of graduates after 5 years, they're in one of those two places. So here we are in Colorado for our design center headquarters. Great universities, University of Colorado, Colorado School of Mines, Colorado Fort Worth, great universities. Big aerospace industry here in this state. We're in Florida, so all of those really good universities. University of Central Florida, Florida Institute of Technology, awesome. Georgia Tech is nearby. We're out in California, so USC, Cal Poly, those universities. And then we deliberately go out to places like MIT, Cornell, Purdue, Penn State's another good one, and so on.
What's the tenure of your average engineer?
Our retention rate here, it is in fact more like 15 years.
Wow.
Yeah, some of the newer companies in our space industry that are more tech-like and have tech roots, they have much shorter turnovers, as short as maybe 18 or 20 months even. Personally, I don't think that works super well because of how long the product life cycle is. You need continuity to get the thing into flight, and you need to do one or two to be really, really good at it.
It's fascinating to think about how much the people, you value the value of the people and the expertise in your industry is as much as the IP in general.
It is so important. And I said I would come back to it, so I don't want to forget. The culture that you have in your team matters a lot too in this industry, because the things that we do are really hard. They are risky, right? So, if your iPhone, blue screen's on you, it's not the end of the world. But when you have a bad day on a launch pad, you're pretty much on the front page of the paper for a while. So there isn't a lot of margin for error there. And then, the missions you're doing are real, even the commercial missions are just so impactful to your customers. So you got to have the right culture around caring about how important the work is and going the extra mile to get it done and really focusing on that customer and what they need. Because in some cases, lives depend on what you're doing. And culture is something that leadership owns. If you go to a company and they have a really crappy culture in their workforce, you can lay that at the feet of the person in charge because they really set that over time.
You guys are a partnership between Lockheed Martin and Boeing. But, realistically, if you're not an industry person, I mean, you stay pretty low key. Is that on purpose? I mean, is it, do you keep the fact that you're a partnership between, Lockheed and Boeing, kind of low, on the down low for a purpose? Do you see some?
So we two different things. I'll say we are the quiet company.
Mm-hmm.
That we try and focus on doing it. And also because we don't use external investment. So we don't need to be touted in the public, in the investment community. So that's the one thing. The other thing is just a reality. So the way you expressed it, when you say you're a partnership between Lockheed and Boeing, joint venture, many joint ventures are two companies that come together and they team up on something. Mm-hmm. So that's what people assume. We're not actually like that. We're a company owned by Boeing and Lockheed, 50-50. So we got like two shareholders, but there's no going back and forth. Everybody who works at everybody who works at ULA works for ULA. And when the company was first started in 2006, it was a Lockheed product, Atlas, and a Boeing product, Delta. All those people had to quit and retire or quit from Lockheed and Boeing and be rehired by the ULA entity. And that's how we operate here 11 years later. Mm-hmm. And most of my employees never worked at either of those companies. We're really standalone. So it's our own employees. We own our own IP. We own our own facilities. It's our rockets. And now there's a new rocket that is neither of the heritage rockets. So it's a little bit different. And so it would be misleading if I ran around and said, well, this is Lockheed and Boeing teaming up to do this. It's not. I have a board of directors. I meet with them 4 times a year. And, we have there are investors and owners, and we have that financial relationship with them, but that's it.
When's your next launch?
Well, hopefully very, very soon. So we just launched our second Kuiper mission on an Atlas. We're going to pivot over and fly Vulcan. We're going to do it for the government 2 or 3 times in a row, depending on what they'd like to do. They haven't announced the date yet, so I can't tell you, but it's hopefully it's really soon. And then after we've flown those, we'll swing back to Kuiper, to Amazon, but now on a Vulcan. And that's really exciting for us, and I think for them too, because a Vulcan is almost 2 Atlases worth of Kuiper satellites. We got 54 for them on orbit right now. We want to add another 45 and then fly a bunch more for them and, get them really close to offering their service.
I love it. We've been on about an hour. Why don't we call it here, Tori? You got a lot of great stuff. I want to have you come back on. And it was phenomenal conversation. I could talk about this for hours, to be honest with you.
Oh yeah, this was super fun. And it's always easy when you ask great questions, Craig. So thank you.
Well, thank you for the time. We appreciate you coming on. Tori Bruno is the CEO of United Launch Alliance. Lots of exciting stuff going on there. So let's do it again.
Absolutely. Look forward to it.